Hi, everybody. Welcome to our colloquium. Today we'll have Gordon Belot from the University of Michigan talking about the Mach-Einstein principle of 1917 to 1918.
Well, thanks very much. It's a real pleasure to be here. Also, yeah, somewhat disconcerting since this is going to be a philosophical talk, also a little bit of an historical talk. We'll see how people enjoy that. So it's part of a larger project, which is I'm writing a sort of philosophical commentary on Einstein's cosmology paper of 1917. So famous paper, which Einstein did many things. He introduced the cosmological constant. He presented the first relativistic cosmology. He made some interesting missteps. He also structured the paper around an interesting and novel argument for the finitude of space. Something, you know, a position that had not been popular for several hundred years before he wrote. So here's how the argument for spatial finitude goes. First premise, I think this one comes from the first sentence of the paper. We must supplement the differential equations by limiting conditions of spatial infinity if we really have to regard the universe as being of infinite spatial extent. Then he thinks, well, look, there's an obvious way to do that, and that's to require this space-time geometry to look more and more like Minkowski geometry as you go out to spatial infinity. But that's a bad idea, he says. For the one thing, it would violate general covariance in a certain sense. For another thing, it would violate Mach's principle in a certain sense. For another thing, it would make it impossible to have the kind of eternal universe that he imagines you should have, in which there's only a finite amount of matter. And then he thinks, this is maybe the least explicit part of the argument, that there are no other acceptable boundary conditions. So we should think that space is actually finite. We should abandon the idea that space could be. So I'm interested in each of these premises of this argument. The sort of thing I'm working on has a chapter or a long chunk about each of them. Today, I'm going to focus on the Mach principle part. The general idea for the commentary is that I'm interested both in the details of what Einstein was doing and why he was doing it and exactly what he was thinking at this stage. It's a sort of interesting period when he's just presented general relativity in the final form, and he's writing papers presenting applications of the theory, and he's also writing a copious amount of correspondence in which he's trying to explain and promote the theory to friends and critics. So I'm interested in that aspect. And I'm also interested in the extent to which the questions he was interested in open up into questions that we're still interested in. So I want it to be a sort of backwards and forwards looking discussion in each case. Okay, so more background. I mean, famous aphorism of Misner, Thorne, and Wheeler, I guess probably really Wheeler. Space tells matter how to move, matter tells space how to curve. I mean, I think this is something that very few people would complain about now as a sort of one sentence, or is it even a sentence, a very brief summary of what general relativity is. But it's not Einstein's view. Okay, so Einstein's view is something more like matter tells matter how to move. And this became clear already in 1913. He's writing to Mach. They had just a little bit of correspondence. So Einstein's deeply involved in trying to construct the new theory, but doesn't yet know how it's going to go in detail. It seems to be absurd to ascribe physical properties to space. The totality of masses produces the metric field, which in turn governs the course of all processes, including the propagation of light rays and the behavior of measuring rods and clocks. He certainly doesn't. The sort of dualistic picture that you find in Misner, Thorne, and Wheeler is unappealing to Einstein. Okay, so that's sort of going to be the thought that we're going to be following today. Now, the way I presented it 2 slides ago, I said, oh, in the 1917 paper, he presented this argument, and one of the premises was asymptotic flatness is bad because it conflicts with Mach's principle. He doesn't use the phrase Mach's principle in that paper. It's in 1918 when he's having this back and forth with Kretschmann about general covariance, and at the same time with de Sitter about de Sitter space-time. He starts talking about Mach's principle in a particular formulation. So this is from the reply to Kretschmann. The G field is completely determined by the masses of the bodies. Since mass and energy are, according to the special theory of relativity, the same, and since energy is formally described by a symmetric tensor, it follows that the G field is conditioned and determined by the energy tensor of matter. Now, he only introduces this formulation in 1918, but he says explicitly when he does so that he's been structuring his thinking about general relativity for several years around this idea. He just hasn't been able to put his finger on it. He's been running it and general covariance together and calling them both the principle of relativity, but now he pulls them apart. Okay, so a few things to note about this version of Mach's principle. It's nothing like anything Mach ever said. Einstein had other Machian thoughts before 1916 and after 1918. So this is just a brief period in which he thinks of it in these particular terms. And it's got nothing explicitly, at least, to do with rotation. Indeed, I think you should just put away all worries about rotation. So this thought is something like specifying what the matter is doing determines what the geometry is doing. And that could be so even if there was rotation. So like Gödel's rotating universe, very easy to specify that that's the geometry you're talking about just by saying a few things about how the matter is behaving because it's such a special solution. That's spelled out there, but we can come back to that if people are curious about it. So I think as a philosophy talk, so there's got to be a distinction between two forms of Mach's principle, even within Einstein's thought. So here's the weak form. Space-time geometry supervenes on the disposition of matter over time. Now, even philosophers, many of them hate this terminology of supervenience. So let me express the same thought in other dialects. These are meant to be direct translations. I think they all say exactly the same thing. So fixing the history of the distribution of matter fixes the space-time geometry. Or there's only one space-time geometry consistent with any given history of matter. Or the degrees of freedom of the total joint theory of matter and geometry are exhausted by the material degrees of freedom, in the sense that if you specify what the material degrees of freedom are, you've specified the matter and the geometry. Okay, those are all supposed to be the same thought. And it's clear that Einstein thinks at least this. Right? So this is the weak form because I'm going to insist, actually, he thinks something stronger, but he does think this. Why am I not satisfied with just saying this is what Einstein's thinking? It's because, well, there's two reasons, actually. I'm only going to talk about one, but you can ask me if you want more about the other one. So one way to specify the disposition of matter is to say there is none, ever. So what does the version of the Mach principle from the preceding slide say in that case? It says, well, there can only be one geometry that's consistent with that. Okay. But that's not what Einstein wants out of Mach's principle. So in his reply to Kretschmann and in other related documents from around the same time, he asserts that the original field equations without the cosmological constant violated Mach's principle because they allowed a vacuum solution. He's thinking, if you're serious about Mach, you must write down a field equation that has no vacuum solutions. The original field equations are ruled out for that reason. So he can't be just thinking the weak version of theory of the Mach's principle, since that's consistent with thinking it's okay if there's a vacuum solution as long as there's only one. And if you're very quick at reading fine print, you can see that there's a whole tangle of people who had similar thoughts around the same time. They were thinking about the Einstein field equations in a very different way than we do, even though the analogy with the wave equation guided Einstein in the search for the equation. He didn't exactly think of it as a wave equation. If he had, he would have thought there'd be lots of vacuum solutions. It didn't. Neither did Hilbert. So there's something fundamental there about the difference between the way we think of it and the way they did. So in a paper submitted the next day in his controversy with de Sitter, says, if the de Sitter solution were valid everywhere, it would show that the introduction of the lambda term, the cosmological constant, did not fulfill the purpose that I intended. Because in my opinion, the general theory of relativity is a satisfying theory only if it shows that the physical qualities of space are completely determined by matter alone. Therefore, there can be no metric field. That is, no space-time continuum without any matter. Right, so this is a thought that you can trace back earlier into Einstein's writings. So in his correspondence with Schwarzschild in January 1916 about the Schwarzschild solution, which Schwarzschild has very, very quickly found after hearing what the field equations are. Einstein says, I can be put jokingly this way. If I allow all things to vanish from the world, then following Newton, the Galilean inertial space remains. Following my interpretation, nothing remains. And so here's another jokey way of putting it. For Newton, space and time were emanative effects of God. And for Einstein, space-time is an emanative effect of matter. Whatever that, you try to figure out what emanative effect means. Nobody has ever known, but that's my joke. Okay, Einstein, even after he gave up on this view, stuck with the joke. So this is a kind of thing that sometimes it makes it hard to know when Einstein has changed his mind, because if he's got a line that he thinks is funny, he'll keep using it even after he's given up on the underlying doctrine. So when he arrived in New York for the first time in 1921, he was mobbed by reporters. And this was the headline in the New York Times the next day. Good. Okay, do we want something stronger than the weak Einstein principle? What? Well, there's some text from 1920 that provide some kind of guidance, I think. I think hasn't completely given up on these ideas. And I guess this is from a letter to Schlick. According to the general theory of relativity, physical space has reality, but not an independent one, in that its properties are fully determined by matter. And in an unpublished manuscript the same year, so space or ether, this is a period when he starts talking about ether again as a good thing, but he seems to mean space-time or the metric or something. Is by no means homogeneous, and its state has no independent existence, but rather depends upon the field generating matter. Since the metric field can no longer be separated in the new theory from the physical facts proper, the concepts of space and ether flow into each other. Since the properties of space appear to be conditioned by matter, space is no longer a precondition for matter in the new theory. The theory of space can no longer be treated before or developed independently of the mechanics of gravitation. And so there's some deep feeling here that it's, he's explicitly telling us it's not that space or time or the metric don't exist. They do, but they somehow owe their existence to matter and their form to what matter is doing. Okay, so he seems to be wanting something like this, the thing in blue. Facts about space-time geometry supervene or are determined by facts about the distribution of material bodies. Because, so far that's the weak Mach-Einstein principle. Then you add something. What you add is because the former sort of facts are wholly explanatorily dependent on the latter sort of facts. So facts all around, but some of them are more fundamental or ground than the others. Okay, so I mean, I would sympathize with non-philosophers who feel like this doesn't really say anything that different from the first one. I think it does, but the difference hangs on questions that philosophers care about more than normal people care about. So what this amounts to obviously depends on how we understand explanatory dependence. And one thing I want to claim but not argue for in the slides, you can ask me for the bonus slide if you want to see the argument. I claim that despite what his phrasing sometimes suggests, Einstein would not be happy to say space-time causes, or sorry, that matter causes space-time or is causally responsible for space-time. So there is some distinct kind of explanatory dependence here, distinctive kind of explanatory dependence that's not causal. So that's enough hints for philosophers to know that I think Einstein is a relationalist in something like a Leibnizian sense, and maybe the same kind of sense you get in among contemporary metaphysicians like Dasgupta, North, and Schaffer, who all want to phrase reconstruct relationalism in terms of grounding. Good. Good. Okay, so that's the end of let's draw distinctions part. And in fact, from now on, I'll mostly, for the most part, you can just picture we're talking about the weak form of the Mach constant. And the question I want to ask now is, well, okay, so Einstein thought general relativity was a theory in which the Mach-Einstein principle actually held. To what extent is that true? To what extent is it true that in general relativity, the distribution of the matter determines the geometry? So easy case, oh, sorry, this is still stage setting. And I guess I want to say, when, in general, when you have some big question about general relativity, like you often find the answer is like, if it's a universal claim, like everything is like this, almost always the answer is like, no, there's counterexamples, right? And then it's interesting to find out what those range of counterexamples is, what the scope of the counterexamples are, what kind of features, physical features you need to make a counterexample. So, there will be counterexamples. Let's try to figure out how broad they are and what underlies them. Okay, so easy case, the vacuum, right? So we haven't escaped the problem that there's lots of vacuum solutions. And so even the weak Mach-Einstein principle is violated. So, and again, one way to specify the history of massive matter is to say there is none ever. That's consistent with many different space-time geometries, even with or without lambda. So the Mach-Einstein principle fails unless we're willing to say, to add to our textbook, yeah, and the vacuum equations are unphysical. Which might seem like a very high price to pay because so many of the tests, classic tests and so on, involve vacuum solutions. On the other hand, you could think like, well, general relativity is in real trouble if there isn't a non-vacuum solution that has a Schwarzschild exterior outside of some, of course, in that case there is, but what about Kerr? Like, we're in big trouble if there isn't something that looks pretty close to Kerr, pretty close to the surface of the sun. So that would be the spirit. And people at this time were doing the same kind of thing for Maxwell's theory. So blanking on his name right now. Doesn't matter. And Lawrence will be the other half of this team. So Lawrence had an interpretation of electromagnetism, which was basically what to throw away all the vacuum solutions. I think that was the end of doing that. Okay, so here are some positive results. Cases in which I think you can make a non-trivial case that there's a sense in which matter does sometimes determine geometry in general.
So matter means mass energy, but it excludes, so now I'm violating the historical Einstein, but it includes black holes and gravity waves, things like that?
No, I'm gonna say no, not that. So I mean, at this period, like Einstein was adding footnotes to his expositions of general relativity, saying like, when I say matter, I mean not just like fluids, but also the Maxwell field. And I'm thinking that's where I'm drawing the line to. So yeah, we're going to put if it's all geometry, it goes on the non-matter side, and anything that we'd be tempted to write down a stress energy tensor goes on the matter side. Yeah.
So even if it.
So yeah, it's going to turn out to be crucial in a few minutes. So black holes don't count as matter.
Okay.
When we get to the counterexamples. Yeah. No, I think that is important. And and when later in his life, the later Einstein denounces the early Einstein for having ever believed this Mach's principle stuff, it's partly because he feels like the Machian mindset took far too seriously a hard division between what counted as matter and what counted as everything else. Okay, good. So let's talk about the one body case with no cosmological constant. That seems like a nice simple case we might be able to investigate. So, and let's say we're talking about a static, isolated body, of finite spatial extent. So here's one thing we can do. We can have some perfect fluid, blob of it, and we fix some equation of state, some easy to work with equation of state, right? And then we have some results, right? So if the exterior is asymptotically flat, then the solution has to be spherically symmetric. So that's a result that took people a lot of work to prove, but it's true. And then this one's not as hard, but if you have a world tube of a spherically symmetric blob of perfect fluid with a reasonable equation of state, and you fix the value of the maximum value of pressure within the body, then that geometry can be matched onto a unique spherically symmetric and asymptotically flat exterior. So If we assume that the exterior of our body, let's just call it a star, is asymptotically flat, then specifying the central density determines unique interior and exterior metrics. So I didn't have to give you much information at all about this. I had to say, it's perfect fluid. It's got this equation of state. Here's finite and spatial extent, because I didn't put in. Well, I don't. Here's the maximum value of pressure within the body, and I had to assume the exterior is going to be asymptotically flat. Okay, here's a different strategy. I'm going to think about an elastic body. So the preceding slide, of course, had this feature that was a lot of symmetries. We want time independence. We're interested in static bodies, but we don't necessarily want anything to be more symmetric than that. So let's consider a more promising setting for getting rid of the symmetries, an elastic body. And so start out with an elastic continuum, finite extent, with no gravity. Then it turns out, this is a sort of implicit function theorem argument. It turns out that for any sufficiently small value of the gravitational constant, there is a unique solution where you get a stressed elastic body that's self-gravitating for that value of the gravitational constant, and everything's vacuum and asymptotically flat outside. Okay, so again, I mean, we had to give more information this time, but the information we gave was about what the body would be doing if there were no gravity. It was just sitting there in flat space. Okay, so the moral is, if we're able to prove or willing to just stipulate that the geometry exterior to an isolated body must be asymptotically flat and be static if the body is, then the Mach-Einstein principle holds for certain kinds of isolated bodies, which are so let's set aside the worry about asymptotic flatness. So there, the interesting question is, does a vacuum exterior for an isolated body have to be asymptotically flat? What other kinds of asymptotic behaviors are possible in general could be? It turns out it doesn't have to be asymptotically flat. There's interesting counterexamples there too. And I'm talking about that in the question period, but otherwise let's step that aside. And let's think about the symmetry thing, where the exterior had to be static if the body was. I mean, that is certainly just somebody around 1918, that would have seemed very plausible, right? Because you've got the static body and it's sitting there. And if there's some dynamical behavior out in the geometry, it's eventually going to affect the static body and ruin its time translation certainty. So presumably the exterior has to be static too. That's the train of thought. Won't it? And the same thing would probably go for spherical symmetry. Like if it was spherically symmetric, but the exterior wasn't, like eventually something would show up and ruin the news of asymmetry in the outside world would arrive and ruin spherical symmetry in the center. Okay. So I'll get to some counterexamples in a minute that exploit the fact that even though that was a natural thing to think in 1918, it's not actually true in Charles. But first I want to talk about this Einstein versus Einstein situation. So as I said, later in life, he came out very strongly against Mach's principle and against his earlier self. So here's a little anecdote illustrating that this wasn't a secret. So Dennis Sciama went to visit him in April 1955. To help ease my tension, I started the discussion with a prepared sentence. Professor Einstein, I would like to talk to you about Mach's principle. I've come to defend your former self against your latter self. Ah, yeah. That is good. Okay. So Einstein himself presumably appreciated he'd undergone this trajectory. It's pretty explicit in the autobiographical notes that he writes about himself in the Schultz volume, but especially in this letter to Felix Pirani. So this is Einstein. Mach sought to abolish space and replace it by the relative mutual inertia of ponderable bodies. That certainly did not.
The space, does he mean absolute space, or does he mean what do you mean?
Yeah, so I think when he's talking about Mach, I think that's all he means. that he was, I think in Einstein's mind, what Mach wanted to do was somehow get rid of what Mach considered objectionable in Newton, but keep certainly the fixed Euclidean structure. Einstein again in 1955, or 1952, when people speak today about Mach's principle, they don't mean to abolish the continuum, i.e. to just make it a action at a distance theory between a few particles, but to preserve the field. But they think that the field ought to be completely determined by matter. This, however, is a ticklish affair. For if the stress energy tensor is supposed to represent matter, it always presupposes the metric. Right? So, I mean, let's come back to this point in a second. So in my opinion, we ought not to speak of the Machian principle anymore. It proceeds from the time in which one thought that the ponderable bodies were the only physical reality, and that all elements that could not be determined by them ought to be avoided in the theory. I'm well aware that for a long time I too was influenced by this idea of physics. Okay, so that's pretty explicit. It's not, I think maybe the best formulation of the main underlying objection here is due to Jürgen Ehlers. If you have a stress energy tensor but not a metric, that does not meaningfully describe matter. There is no theory of physics so far which can describe matter without already the metric as an ingredient of the description of the matter. Therefore, within existing theories, the statement that matter by itself determines the metric is neither wrong nor false but meaningless. Okay, so, I mean, to drive the point home, like think about something as simple as dust, right? Even there, the stress energy tensor, it's just like the mass times the forward velocity times the forward velocity. The forward velocity, of course, is normalized using the metric. Right? It doesn't appear there explicitly, but it appears implicitly, even in the simplest form of ponderable matter. So how, this is sort of my reconstruction of Ehlers' reconstruction of Einstein, but I think it is true to the thought behind Einstein's concerns that he voiced to Karani. So matter enters the field equations only through the stress energy tensor. Therefore, to say that matter determines geometry is to say that there's only one metric consistent with a given stress energy tensor. But the stress energy tensor depends on the space-time metric as well as the variables describing the matter content of space-time. So in general relativity, it makes no sense to speak of some way that matter might be distributed as determining or failing to determine the geometry of space-time.
So in a way, this is all about what the equal sign means in the Einstein equation.
Yeah. Yeah. I mean, and I think that argument as stated can't be sound because, as I keep saying, it makes sense to say there's no matter. And then I don't have to presuppose anything about the metric tensor to write down the stress energy tensor. Just write equals 0 now with 3 bars to make it identically equal 0. And I mean, so that's a kind of narrow point. But more broadly, and I think more importantly, we've just seen some tricks for specifying the matter dense distribution that don't involve directly specifying the stress energy tensor. So the objector, starting with Einstein and going through Ehlers, is imagining that, oh, when you say specify the matter distribution, you're saying, here is my stress energy tensor, find me the metrics that go with it. That's a silly game. And the truth is, you don't have to specify the matter distribution by specifying the stress energy tensor directly. Of course, you specify it indirectly, and thereby you indirectly specify the metric tensor. And so there's a sense in which, in saying something like, I got a blob of perfect fluid with this equation of state and this central density, you have given all the information about the metric tensor, but that is the point of Mach's principle, and not objection. So for instance, I think I can say, I've got a blob of polytropic fluid. This is the maximum of pressure inside it, without saying whether I'm talking about Newtonian physics or general relativity. So I certainly haven't specified the space-time metric when I've specified that information. Of course, once I specify the field equations I have, that was the point of Mach's equation, that once you said what the matter was and you imposed the field equations, then you had specified the geometry. Okay, now there's a kind of worry here, like, is it the same pressure in Newtonian physics and in general relativity? It's a good question. I don't know the answer. I think it's a genuinely hard one. I think it also doesn't matter here, like the fact that there's the quantity, even if it's two different quantities, they're playing the same functional role in these two theories, not to make the reply work. And I think there's also a fallback. So the worst case would be, in order to specify the matter configuration, I have to specify the matter and geometry within the world tubes occupied by matter. And then there's still a substantive question, what could be going on outside? Right? And indeed, in the early history of general relativity, like Painlevé thought he had found a knockdown argument against general relativity because he thought he had shown that there were two possible exteriors for a ball of fluid. Turned out he was just looking at a Schwarzschild solution in two different sets of equations, but the point is that's a non-trivial test to show that there aren't two exteriors for a single ball of fluid. Okay, now for the counterexamples. So one set of counterexamples is just driven by the thing that Einstein thought was going to help them, the cosmological constant. Okay, so left to its own devices, it drives exponential expansion, and that can make it hard. If you were like living on this curve here, it would make it hard to know about everything that was going on over there. And so there could be, for instance, things could be symmetric over here in a way that they weren't over there, and you would never find out about it. That's sort of the basic underlying thought. But here's a way to make it precise. So fix lambda, make it positive. Consider now it's natural to consider, instead of us like a world with one isolated star, to consider a world where there's two isolated stars on opposite sides. Or you can do a symmetry thing and quotient out and make the spatial geometry projective instead of spherical, if you want. Okay, but the point is, here's a picture where we have these two static stars that are just sitting there forever doing nothing. Each of them is immersed in a vacuum which is static nearby, but not static far away. And so this is just a basic fact about how vacuums tend to behave when lambda is positive, that it's very hard to make static solutions, but it's easy to make solutions that are static in neighborhoods of bodies. So up here and down there, we have exponential expansion or contraction. Here we have these stars are just like living in a box as far as they're concerned. Now, the thing about that is just saying what the stars are doing does not fix the exterior geometry, because this is the same geometry for the matter, but with a black hole and a white hole pair interpolated in between. And in fact, you can do this trick as many times as you want, or you could just have one star with infinitely many black holes in a chain. So fixing what's going on with the matter doesn't fix the exterior geometry here, and it's because we're not counting black holes with that. Okay, here's another example without lambda, but also no longer static. We've got collapse. Just put it like this, right? So we've got, here we are, instant of time. We've got time reflection symmetry. The red part is the matter that's at rest everywhere within the blob at this time. In the future direction, what happens? Well, the blob is just it's just fluid, it's going to collapse. It's going to collapse into a black hole. Right? So we get this singularity up here. It was time reversal symmetric, so actually the blob came out of a white hole. So if you're on this slice where everything's time symmetric, like if you're not too far out, you can send signals to the ball, people living on the ball, and tell them like, oh, you're collapsing into a black hole. But if you wait too long, of course, your signal won't reach the ball, anybody on the ball before it's collapsed, and you'll just be sending your signal into the black hole. And also the time reversal, of course. But out here, you can neither, if you go out far enough, you can't signal the ball at all, either in the past or the future. And the idea is, okay, let's fiddle with the initial data only out there and make a solution where this portion is always the same. It can never find out about what happened out there. So we'll have two solutions, same behavior of the matter, different overall space-time geometries. So of course, it's not completely obvious we can do that, right? I mean, that because there's non-trivial initial data constraints, it's not obvious maybe like physical intuition may make it like very, very plausible, but it's not completely mathematically obvious that you can actually write down an initial data set that differs just out here in the right way to say symmetry, spherical symmetry. And this is another curious point of the history that around this period, Einstein thought you could just glue flat region on out at spatial infinity. That's not right because of positive mass theorem. And it's curious because the very paper in which he says this is the paper in which he is writing down the ADM mass for the first time. And Felix Klein writes to him and says, like, what's going on? Like, it looks like it's just like electromagnetism. You should be able to find out about the charge in the center by integrating over large spheres. And Einstein insists that, yeah, that's true in electromagnetism, but not in general relativity. It's a very confusing exchange. Okay, it's not obvious, but you can do it. Okay, so these various gluing results, like the workhorse of gluing results due to Corvino and Shane, like what you do is that you glue like a Kerr-like region at spatial infinity onto anything in the middle. That wouldn't help us in this case because it would just coincide with the thing we started with. But you can fiddle with the gluing results in a way that allows you to put initial data in a neighborhood of spatial infinity for our setting that is non-static. And then it can't be spherically symmetric since it's not static because of Birkhoff's theorem. So what we've created is a solution that overall is not spherically symmetric, but is spherically symmetric throughout the entire region that can communicate with the matter. And so it's going to be a counterexample to a bunch of things that we were thinking before, because the matter is static, the matter is spherically symmetric, but the exterior is neither static nor spherically symmetric. Okay, so where does that leave us? Well, it leaves, honestly, I think it leaves us with a bunch of questions that I at least think are interesting. So one question is the philosopher's question. What exactly does Einstein's Mach principle require beyond the weak Einstein Mach principle? But some of the other questions are more like physicists or mathematicians questions. So maybe this one is for physicists and philosophers. So in general relativity, what are the acceptable ways of specifying the material degrees of freedom upon which the geometric degrees of freedom are supposed to supervene? And so I gave a couple tricks that I think work. People may disagree with those, so that's a point at which they could there could be an argument. But I think it's also like, yeah, trying to come up with other more general ways of specifying the matter configuration without obviously directly specifying the geometry. So now the counterexamples I just gave to the Mach-Einstein principle both involve observer horizons, right? So there's basically the world tube of the matter as it looks back in the past can never see a complete slice of any Cauchy surface. Once you've seen some examples like that, it's kind of obvious that that is a way to create counterexamples to the Mach-Einstein principle. And I think, of course, it wasn't obvious to anybody in 1918 that phenomena like that could occur. That's part of the wonder of general relativity in the coming decades. But I think it's also natural to ask whether there are other global structures that could make it easy to create counterexamples beyond observer horizons. Another obvious question, like what if we have rotation, a rotating body or multiple bodies? And then this one that I said earlier I didn't want to talk about more today during the slides, which is true. What range of asymptotic behaviors at spatial infinity arise for exteriors of static bodies in general relativity? So I know one other possibility, but I'd be very interested if people know more about this class, especially. Great. Well, thanks very much.
Okay, so if anybody in person or on Zoom has any questions, please raise your hand.
Let's see the asymptotic behavior.
Oh, yeah. So here's a nice one. So yeah. So this is something like in 1917 already. Levi-Civito was finding a lot of exact solutions, and one of the ones he found is you've got an infinite cylinder of perfect fluid. So it's axisymmetric, I guess we could make it translation along this axis symmetric as well. Make it symmetric as well. But anyway, we've got an infinite cylinder of fluid. Okay, so this did not like excite physicists very much. I think they may well have thought like, yeah, we don't have infinite cylinders of fluid, but it's worth thinking about like what the vacuum exterior for that is going to be like. So, it's the analogy, the general relativistic analogy of an infinite line of charge in Maxwell's theory. Right? And what happens if you have an infinite line of charge? Well, the potential behaves diverges logarithmically at spatial infinity as you go away from it. And so infinite escape velocity. Right? No matter how hard you fire a charge away from it, it can't escape. It always has to come. Okay. Same thing with this. As you go away from the cylinder, the metric, the metric, like the Kretschmann scalar, say, goes to 0 if you go out perpendicular to the cylinder. So there's a sense in which like all the components of any curvature tensor you can think of are going to go to 0 as you go out, but not fast enough to count as asymptotically flat in any ordinary sense, because, on the one hand, there's this direction in which never the curvature doesn't change at all, but also because it's not going to satisfy the right fall off, even in the directions in which it does fall off. It's not going to satisfy the fall off conditions strong enough for you ordinarily to think, I've got asymptotic flatness, because you still have the infinite escape velocity. Okay, still an infinite cylinder. Okay, we don't think that's physical. Okay, yeah, but if it's translation symmetric, just take 2 slices and identify. And now what we've got is fluid torus, perfect fluid torus, no rotation, nothing tricky, no cosmological constant. Can't collapse because it's wrapped around a small dimension. And it's got finite total mass, but there's infinite escape velocity for anything in the vacuum exterior.
And time.
No, don't. Sorry. Yeah, I should have. I wish I could draw things better. So yeah, just within a slice, within a time slice, you perform a quotient. Oh, sorry. I'm thinking like the cylinder is like this. Within a time slice, I take these 2 surfaces. I make the identification that way.
What is U2 quotient?
Yeah. So then I end up with I turned my cylinder. Whatever the distance was between these 2 slices, now I've got a torus where the longest circle is that length. Yeah. There's another, there's a black hole that has the same asymptotic.
And this is the solution with the fluid having some non-zero pressure, which is also sort of constant over the whole cylinder.
Not along the whole cylinder, just along a line, right in wherever the center. So this, So in the infinite cylinder, there's all kinds of equations of state are possible. Yeah, and the same thing, like we just have to say what the maximum pressure is to specify the interior and the exterior once we've specified, right? So, so in fact, earlier when I was saying like, oh, I got a blob of fluid and I specify the maximum of pressure, that does not determine the shape of the fluid. It could be either spherical or toroidal, depending on whether I have asymptotic flatness outside or not.
I have a question on that as well. So you have to say something about the matching the surface, right? That you're matching smoothly, there's no shell and it's
Yeah.
So does the matching not impose conditions on the configuration itself of the interior solution?
Tell me more about what matching you're picturing would.
So let's say you have this polytropic equation of state.
Yeah.
Ball.
Yeah.
This guy will have some energy density, and if you're matching it to an exterior, say curve, at the surface you will have some jump in energy density, which means this.
Yeah.
This will match it smoothly, but how you do that matching will either say that the fluid is rotating because you have to start.
Right.
Things or.
Yeah, right. No, I'm thinking, I'm in the non-rotating case.
Okay.
So I do have to do a matching thing, and some things will be discontinuous, like as they are between the Schwarzschild interior and the Schwarzschild exterior, like there's jumps in some, in a sectional curvature, it's smooth in one of the directions and it jumps in the other direction. So we can't get rid of that, but, I don't think we get any extra weird things by considering the cylinder rather than the ball. Like the theorem I was mentioning before from, I don't remember, Rendell and Schmidt maybe, that's about there being a unique exterior for any fluid ball, basically. That's been generalized to this cylinder case. So we have, yeah, so there's no extra slippage there. But it's certainly, I agree, it's certainly weird to think, yeah, that you could have this torus of fluid that can't collapse. Yeah, and with finite mass with infinite, it is right. There is also a black hole that has the same asymptotics. The Nikolai Koropkin black hole, maybe it's called. So here's how you just imagine you tried to put a bunch of Schwarzschild black holes along a line. Okay, so the horizons would no longer be spherically symmetric. They'd be deformed because they can feel their neighbors, but only in that one direction.
But they can stay static.
They can, yeah. I mean, it's probably not stable, but
Okay.
all right. But you can put them all on a line, and then you do the same quotienting thing, and now you've got a black hole by itself, without a spherically symmetric horizon, and with a non-asymptotically flat exterior. Yeah, general relativity is weird. It's tremendous. Yeah, so I mean that's really, I mean I'm quite I'm very much in search of further examples of this. I mean, so there's this great paper by, I don't know how to say his name, Reris is how I say it in my head, Reiris, from about 7 or 8 years ago now, where I mean he's trying to address the problem of whether the field equations imply asymptotic flatness for isolated bodies. And what he shows is basically if the slices have trivial topology, then it does. But if they don't, then it doesn't. So the black hole version of this example is I got from him, and then I want a fluid, so I altered it.
I have another question on the Markov aspect.
Mhm.
So we now know that you can have Penrose processes
Mhm.
in spinning black hole spacetimes.
Mhm.
So if you take a curved black hole vacuum, you can still extract energy from the spacetime itself.
Yeah.
So there's a sense in which you're actually getting some mass energy out of this thing,
Right.
and the only source is the spacetime itself. There is no matter.
Yes.
So what does this observation tell us?
Yeah, I mean, I think it pushed us in the direction of like Peter and the late Einstein of thinking like, okay, if we were serious about general relativity, then we would not care very much about the distinction between massive matter and geometry. Yeah, and I feel that. I think, I mean, especially, yeah. Yeah, it's not obvious it's going to survive. Even for now, working in general relativity, we have a kind of clean divide. It's not obvious that will survive in the future at all.
Maybe I'll insert myself with a quick historical follow-up. So what changed Einstein's mind? Was there anything in particular, or was it just being the
Yeah, right.
theory?
Yeah, I don't know. So I have a sort of like obsessive relation with Einstein up till about 1920, and then after that, my knowledge is very spotty. So, I mean, one thing that happens, like even in this period, de Sitter, Einstein wrote this cosmology paper and said, okay, we're going to have cosmological constant and finite spatial slices, and that's just going to make the Mach's principle be true. Right? That's so good because without the cosmological constant, we had empty spacetime. That was terrible. And de Sitter immediately says, I don't think that's right. I think you can have an empty space-time with positive cosmological constant and finite spatial slices. And he wrote down de Sitter space-time, and Einstein is sure that can't be right. And he and
It can't be right on these grounds, as to say without matter, or it can't be right because there's something intrinsically wrong with the center space.
I think he thought it must secretly have matter. So yeah, so he and Weil decided that de Sitter space-time actually did have matter. And they had a sort of battle royale against de Sitter and Felix Klein.
Wow.
And eventually Felix Klein, after trying more than once, said, look, it's just a hyperboloid in Minkowski space-time. There are no singularities. And eventually Einstein conceded on those grounds. It took, this is very surprising to me. It took like months more before Weil gave up. So, I mean, you would have thought it would have been immediate for him once he was told about, you know, the geometry. But anyway, they went on. So this went on for a while. What were they thinking? Well, they were, you know, de Sitter spacetime was, you know, of course, it's written down in coordinates, and the coordinate description they liked was the static patch, where the slices of constant t cross, and so there's a singularity there. And so they thought, okay, yeah, that's, you know, it's just like it was natural for them to think, if somebody gives you the Schwarzschild exterior, yeah, okay, it's vacuum, but there's some matter off stage. They thought the same thing about de Sitter. When they were talked out of it, Einstein felt like he had to officially give up on Mach's principle, and then it became something like, oh yeah, but you know, solutions that have a Machy feeling are better than solutions that don't, or something like that. And so it sort of faded away a little bit over time like that. My suspicion is that the this shift towards like, those Machians are so naive with their distinction between matter and geometry may be tied up with his decades of work on the unified field theory. But I'm not sure. So a strange aspect of this story is, I mean, you could write down an electromagnetic Mach-Einstein principle and ask about, you know, do the charges determine the field in Maxwell's theory? And Einstein didn't think it did. He's fairly explicit that that's the wrong way to think about Maxwell's theory. That you know, he liked all through this period the idea that Maxwell's theory isn't really the right theory. There's some kind of like nonlinear thing that will improve on it, in which charges will turn out to be like solitons or something in the field. It's like stable field configurations. So there won't be a dualism between charge matter and the electromagnetic field in Maxwell's theory. He was thinking these thoughts at the same time that he was thinking this way about general relativity, and that turned out to not be a stable configuration. And eventually, it looks like he became all of his internal life converted to this like picture that de-emphasized the duality, the dualism, I should say.
Other questions? Okay, maybe then we can break for lunch.
All right, thanks very much.
Thank you. Okay.
Thanks everyone on Zoom.